Okay. All right, so people are starting to come in. So hello, everyone. I'm Renee Yager, and welcome to today's webinar, Design with GaN Power Electronics for High Efficiency, Smaller, Lower Cost Power Banks, Battery Management, and Regulators. Before we get started, I would like to go over a few housekeeping items. You have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature that you can see at the bottom of your screen. You can send those questions in at any time, and we'll collect these and address them at the end of today's presentation. So now let me take a moment to introduce our speaker today. Andrea Gorgerino is the Director of Global Field Applications Engineering at EPC. He is an engineering leader with several years of professional experience in leading design and development of power electronics products, including hardware and firmware. Andrea, thank you so much for joining us today.
All right. Hello, everybody. Welcome to the last one in this GaN for Consumer Application series. Again, today we're going to talk about mainly power battery applications. So this is a very important trend, I would say even a mega trend in the market. So let's dive in. So we'll talk a little bit about the market trends, why this is an important applications. We'll go over a few typical applications and solutions that we are targeting with our products. And then we'll dive in a little bit of the GaN topics with some of the GaN benefits, as well as some more specific details about the back-to-back topology, which is a very common topologies in these battery applications. So just a little background on EPC. So EPC's market share is more than 80% in the under 400 volt market for the GaN ICs and discretes. You can see these two charts, basically they tell the story. You have basically on the left-hand side, discrete GaN devices. On the right-hand side, you have IC GaN devices, and the x-axis is the voltage classes of the devices, and the dots are basically the products that are out there, of course, the current rating, but mainly just to represent, in the 400 volt and below, which is where EPC product range lies, is dominated by green dots, which are the EPC dots. So we have more than 80 devices available, including several automotive one. And that means today we will talk about applications, of course, where these products can be used. So battery applications are becoming very, very common through a very broad area of power. We will focus today on the lower voltage area, very typical, between 48 and 100 volts, I would say, a little bit higher maybe, and maybe up to a few kilowatts of power range, just to give you an idea of what we will be discussing. So in this area that I mentioned, we've seen tremendous growth in the end markets of these battery applications. And this is driven basically by two trends, one on the customer side and one on the manufacturing side. On the customer side, of course, it's simply battery applications are more convenient to use. So there's a strong customer pull for these type of application and converting the application to battery operation. Together with this, there's a demand of increased efficiency and in particular longer battery life, of course, which is usually the trade-off that you have to pay with battery operated applications. There is also an important trend in the last few years for renewable energy sources, in particular solar power to recharge batteries. So that is basically the ability to drive more applications directly from renewable energy. So that's an important trend, and it is definitely made available by these battery applications. From the manufacturing side, we've seen a lot of improvements, of course, on the battery technology, which enable these improvements in terms of user experience, but also on the power management strategies. There's been a lot of development and new ideas, and that's mainly what we're going to focus on today. How do we improve the user experience based on power management strategies? And of course, there's also an optimization of the applications themselves to run off of battery power. And all of these factors basically make that these applications are seeing an extremely high growth. And I think it will continue to be that way for the foreseeable future. So I'm going to give you 3 examples where power management strategy can really enhance the applications. So the first example, this is a very common application. I think now everybody has one or several of these, is the USB PD power bank. So, it started off to charge basically your phone, but not going to charge a lot of things depending how big. It's a very broad range. And an important change that happened actually last year in 2022, maybe even 2021 was actually announced, but 2022 we start to see some real products, is the migration from USB PD 3.0 to 3.1. 3.0 is basically what most people have today in their home. These go up to basically 20 volts. And the 3.1 standard extends the voltage on the USB PD connector with the same USB-C connector up to 48 volts and 5 amps. That's 240 watts of power. So that becomes a very significant amount of power that has to be handled. And in a power bank, you have typically a lithium-ion battery, probably 3 cells in series. That's very common. It could be a little bit more, a little bit less. But in this example, I just showed 3 in series. And that means the voltage range of that battery goes from 9 volts to 12.6 volts. And of course, now you got to match this voltage range from the battery to a very broad range from the USB PD standard, which basically is 5 volt for all the smaller electronics, all the way to up to 48 volts for this new standard. And so at the end of the day, you need a buck boost topology. And the very common one is the back-to-back one I mentioned before. It's basically one leg is a buck, one leg is a boost. There's an inductor in the middle. And the operating mode of this is basically depending on the voltages that are present on the battery, depending on the state of charge, and depending on the user request, basically what is the user connecting to the connector is requesting a different voltage class. It will either operate as a buck with one of the legs, as a boost with the other leg, or as a buck boost when both legs are operating if the two voltages are close to each other. So very important application here and a growing trend for sure. The next one I wanted to talk about is about e-mobility. So these are usually a little bit higher power, and I think what e-mobility basically represents, anything from e-scooters to e-bikes and e-motorcycles, smaller ones, and many other vehicles that are being electrified for this mobility type applications. And the standard way to do this, you have a battery, 48 volts, 36 volts, depending on the power level, very common, maybe 70 volts, as I mentioned here. And then you have a motor that's connected to it. But, when what this means is that in normal conditions, the performance of this e-bike or whatever e-mobility device you're using will depend on the state of charge of your lithium-ion battery, because the voltage will change. So one way to improve that is to add a DC-DC conversion stage, as I've shown, where you stabilize the voltage to a fixed voltage independently from the state of charge of the battery. And this allows you to then optimize the motor, both in terms of size and performance, to a fixed voltage. It makes it lighter, it makes it more performance. And also then it becomes that the performance that you have from this system does not degrade with the state of charge of the battery. Basically, you still can go up the hill even with a low battery. And to do this, what I've shown here is a buck converter. This is typical because you don't really necessarily need to do a buck boost, but different topologies can be used. But this is a common one. You would have a lithium battery, which has a higher voltage than your stabilized voltage. And then you would have a simple buck stage and a stabilized bus voltage here that then drives the motor and the inverter. So this is another interesting application. The last I wanted to talk about is a class D, for example, for automotive audio here. In this case, we have same situation, 12-volt car battery that typically goes from 6.5 to 16 volts, depending on the conditions. So quite wide operating range. And so in high-end performance audio systems, you need a higher voltage to drive the performance, as well as a stable voltage. And actually, sometimes it's an adaptive voltage. It can be varied depending on the requests from the audio system. So it's very important to manage this bus actively versus whatever the battery gives you. So here is basically the idea is you would use a boost converter. You'll take the battery car input, boost it up to your voltage. The range that I've shown here is between 20 and 50 volts. So that's quite typical. And this allows you, again, to optimize the performance of the application independently from the battery and from the operating condition of the vehicle. So I've talked about these three applications to give you some examples of what our customers are doing today. I think the topologies are, these three mainly, although I have to say in general, they are interchangeable. They're not linked to this particular application. I think these are the most common ones. And in particular, the back-to-back converter, the buck boost, is the one that gives the most flexibility. So there's a lot of interest in that particular one. It can be used in definitely all of these applications if needed. All right, so let's dive into some of the GaN benefits for this particular application. So I'm going to start off with some high-level topics here. So one of the main benefits that I mentioned is one of the requirements from users is the longer battery life. And this, by having higher efficiency, is definitely one of the big draws of using GaN semiconductors in these applications, is to extend the battery life. But there are also other factors that are extremely important. At the end of the day, it's power density, right? So when you use GaN devices, you can basically go from, typical switching frequency, maybe 100 kilohertz, easily to 800 kilohertz. And this really gives you two things. One is a smaller volume. The applications that I've shown you are basically an addition that you have to do to an existing battery. So it's a trade-off that you need to do, where in a certain volume, whatever your application has, you can fill it with batteries, or you can fill it a little bit less with battery, and you can add a converter to it to add performance. So that's the trade-off. And of course, if that trade-off requires less volume, it's a much better trade-off. And I think that's why we've seen people really look at these devices to have the advantage of the power conversion topology that I've shown you without adding bulk or having to shrink the battery, which is basically the trade-off. And the other thing, of course, is also weight. Weight, of course, is very important, especially when you increase the frequency. You can decrease a lot of the passives, and that adds a lot of weight. And so weight in battery applications, since they are by definition portable applications, is the other very important parameter when we talk about power density. So these two things are definitely enabled by using GaN devices and increasing the switching frequencies. Another one that I would like to emphasize, though, is the thermals, because again, you're adding a power converter circuit, so that adds a thermal budget. And thermal budget means you have to handle it with some cooling. And the fact that you have a very high efficiency converter allows you to do that with avoiding complex cooling and avoiding additional thermal management things that you need to add to your device. Again, making that trade-off in the battery design better. So let's look at why we can do this. So first, I want to look at a few electrical parameters. This is a comparison using benchmark silicon MOSFET that you can see here as compare against the 2619, which is our latest generation. This is what we call our Gen 6 device. This was announced back in October. It is sampling today, which should be released by the end of the year. And I think this really shows the evolution of GaN and how it's getting better and better. So these two devices are incredibly different. I don't think they're actually exactly to scale, because it's a 30 square millimeters on the left versus about 4 square millimeters on the right. It's much, 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 much smaller. This is actually a higher RDS(on) part, and we chose it on purpose because we want to show what the benefits are when you increase switching frequencies. So this actually is a higher RDS(on) part than the silicon MOSFET. The switching charge parameters, basically you see here, the gate charge QG, the QGD, and the QSS are all much, much smaller, like 10, 4, 5, 10 times smaller, depending on the specific parameter. So incredible improvement in terms of switching characteristics. Also, I want to highlight again, there is no QRR. These GaN devices, they have a third quadrant operating mode, but it's not a body diode. And since it's not a diode, it doesn't have reverse recovery. The last parameter we're comparing here are the thermal resistances. The thermal resistance to the bottom, that means towards the PCB, that is pretty much proportional to the area of the device, right? So of course, we have a very tiny device, so the RTH to the PCB is higher, but we have double-sided cooling. These are chip scale level packages, which means they basically are the silicon substrate, and you can attach a heatsink to it very effectively and get close to the source of the heat very effectively. So and I'll show a little bit more detail of that, but basically in this very small device, you can have 1 degree C per watt. That's same order of magnitude as you have on the silicon FET to the bottom with that huge area. So that's very impressive. So the reason I have these two devices up here is because we actually built two boards, a simple buck converter, just to give an idea, but I think it's perfectly suitable for the application we're talking about today. And we tried to build these two boards as close as possible. They got same size, very similar layout, same inductors, of course, same passives around it. And we ran them in similar conditions. And what you can see here on the left-hand side is basically the efficiency and the power losses in the power stage. The orange curve is the silicon device. And you can see that it maxes out at about 94% efficiency, 94.2 maybe, something like that, at 500 kilohertz. And we ran at 500 kilohertz also the GaN device, and that's the blue curve, and you can go more than 96%. That's an incredible improvement. The other thing I want to highlight is look at the maximum current of the chart, and there's also a table at the bottom here showing the numbers basically. But what you can get from a device that is almost a tenth of the size, you can actually get more current. And again, this is without a heatsink. So if you do that heatsink, that's even more. So just with the device itself, how efficiently this can be cooled. Basically, you can get a maximum of 22 amps with the silicon. You can go up to 24, 25 amps with a GaN and at 400 LFM in this case here. Yeah, so this is very impressive. Now, because it's so effective, we actually are able to run this also at 1 megahertz. So that's the green curve that you see. The efficiency is still better than the silicon at 500 kilohertz, much better, I would say. And so that's where you get the advantage of GaN. You can have higher efficiency and higher frequency at the same time. By the way, on the right-hand side of this slide here, you have the gate driver supply, which was not included in the power stage efficiency, because these devices, the gate charge, if you remember, is so small that the driver losses are also very, very small. And the driver losses, of course, need to come from a power supply. And this is the measurement for the power supply that we're using, the auxiliary power supply. And you can see here, you go from about let's call it 0.8 watts down to less than 0.2 watts, even comparing 500 kilohertz and a megahertz. This is an additional loss that you don't even see on the left-hand chart. So again, all of the same thing, higher frequency and higher efficiency at the same time. So again, and by the way, I did want to say, this is a 3.3 million versus a 2 million device. And again, this is a higher radius on, but still much better efficiency. So that was the electrical comparison. Let's talk a little bit about the thermals. I already shown you the end result. Basically, we can get more current, but I want to go a little bit more detail because it is important to explain why. So this chart compares those two same numbers I was talking about in the first datasheet comparison. Basically, these two charts have on the left-hand side the thermal resistant junction to the board, and on the right-hand side junction to the case. By the case, we mean the top of the device. So on the left-hand side, you have basically a plotting of various silicon and GaN devices versus device area. And as I mentioned, on the bottom, it's pretty much follows this rule. It's inversely proportional to the area of the device, and all the device roughly sit in that curve. So smaller device will have higher RTH. However, on the right-hand side, we see here a comparison for top side cooling, basically. And we're comparing the blue curve, the red curve is actually devices that are enabled for topside cooling, which not all silicon packages have that. For example, the one we were comparing in the first slide does not have that topside cooling availability. So, but for devices that do, even for those, you can see that the blue curve now for GaN is much, much better than the red curve for silicon. And the reason for that is because, again, since this is a chip level scale package, you have no layers, not fewer layers. You have no layers between your thermal solution and the actual device. While even in a thermally topside cooling enhanced package, silicon package, you still have many layers there. And that's what contributes to that higher number. And this is why you can really get these very high power densities if you want out of GaN designs. And there are a few simple methods. So I want to go through them real quick. So the first one is basically what we used in the slides that I showed the test results for the Gen 6, and is using the PCB copper for heat spreading. So the copper is already there. Of course, we want to maximize the amount of copper. We have some guidelines there on how to make these designs. This is our traditional designs, basically. But you want to use this copper to conduct the heat flux, and you want to use all the layers to do that. And so one way, of course, if you have no vias, basically the inner layers are not being used effectively for conducting heat. So we want to add thermal vias. And you can do that, as you see in the center picture, by using side vias, which are somewhat easier to manufacture. And of course, you want to add a lot. This is one design examples where we basically put them all around our devices. Or what we do in pretty much all of our designs, we use vias under bump. And I'll show you in one slide about what the difference is between these different methods. But you definitely want to use thermal vias to do high performance designs. And then the next thing you can do, of course, is utilize the topside cooling. So we have a very easy way to do that. We have this in most of our reference design availability, basically to add a heatsink. The way to do that is quite simple. We have these little spacers here. These are SMD spacers, so they get mounted as on any other component on the PCB while during the PCB assembly, basically. And once you receive those, it's very easy to mount a heatsink. You basically just add the thermal interface material. Now the choice of the TIM is important. You want to have a high performance TIM material here, but even those are a little bit expensive sometimes. The advantage is that the area that you need is extremely small, because these devices are so small. You need very little amount of these TIM interface materials. So basically, at the end of the day, the overall cost is very, very small. And then you add the heatsink on top. You just mount it with screws, and the standoffs provide the height and the compliance versus the PCB and the devices, and they provide the compression to the TIM. So it's an extremely simple assembly method. We have many examples of exactly this approach in our reference designs and demo boards. So the thermal summary, and when we put all of this together, I put in here a few numbers to show what they are, what you can expect. So more than looking at the specific number, what I want to say is basically the percentage differences between different approaches. By the way, this was done using our online GaN FET thermal calculator tool. I have the link here, so I encourage you guys to take a look at it. It's a very simple tool that allows you to choose the devices and input basically what kind of thermal concept you will use, and will give you an idea of what the expectations are. So it's very useful to trade off some of these different approaches. Anyway, the end result is, so the vias under pads, I use that as a baseline because that's what we normally use for our references. If you go from the under the pad vias to the side vias, you'll lose about 7%. And if you have no via at all, you lose about 25%. So that's a significant change. And of course, when you add a heatsink, now we're talking completely different levels. It's about 5 times less the RTH, right? So you can really push the power density. You will go to this heatsink approach. All right. Okay. So that was the thermal one. And I want to show some pictures. Again, this is going back to the Gen 6 results. These are, by the way, the two boards on the right. These are, you can see here on the top, the GaN FETs on the converter, very tiny GaN FETs with a driver next to it, and on the bottom, the QFN packages. So there was no room to put the driver here, so we put it on the other side. So very different area that is needed for both, and also the layout actually. At the end, is much harder to optimize the layout with these packages. You can see they're a little bit offset. It definitely takes on a bigger area and harder to make a layout, but the two boards were actually basically identical. And this shows the thermal pictures of what I was already mentioning. Basically, you can get to higher currents with the GaN device in exactly the same conditions, even with a device that is almost 10 times smaller. You see the picture here. The one in the middle is 22 amps, both of them at the same conditions. The silicon reaching 104, and we use 105 as a typical limit for PCB temperature. I think that's a very common limit. And on the top, we reach only less than 90 degrees with the GaN FETs. And that means basically we can push this all the way up to 25 amps. And 25 amps, you'll reach about 106 degrees C. So again, this is basically to show how even with these extremely small devices, you can get very good cooling if you follow these simple guidelines when you design your PCBs. Okay, so these were kind of generic topics. And so now I want to talk in particular about the back-to-back topology. This is the buck boost one. I think it, as I mentioned, this is a very popular topology that is very flexible. And so because of these large variations of battery voltages and the applications is becoming very popular for battery applications. So the first one I want to talk about is an example from Richtech. Richtech is an IC supplier. They have basically controllers for this topology here. This one is clearly targeted for power banks, mobile phone chargers, etc. This is the new version that supports PD 3.1 up to 36 volts. So it's interesting because they had an original design on the top. You can see it there. I circled the red, the area of the power section, basically, and you can see the large inductor and the 4 QFN FETs around it. And if you see my mouse, that's the area right there. And we redesigned it, in the bottom one, that's the new board with a much smaller inductor and a very tiny GaN FETs that I can't even see exactly. The resolution is not good enough. And you can see basically we were able to shrink by half the power area while increasing efficiency. We reached more than 88%, 98% efficiency in the 20 volt to 12 volts. So very nice example of power bank application. This is the APC 2204, which is a 100 volt, 6 milliohm device, very small, 2.5 millimeters by 1.5 millimeters. This is on our Gen 5 platform. So talking about this application, I wanted to show a little bit some calculations on how you would optimize the devices for this. So I've taken a slightly different example. So this is using a 40 volt device for basically what would be a more USB PD 3.0. And we're comparing here same topology where we have a 12 volt battery in this case, and going out with a buck boost topology for a USB PD type application charger. We want to compare here an Infineon MOSFET here that you see here, and the EPC 2057, which is a new device that is under development. It's just a smaller device basically that's optimized for this application. You can see here it's a very small device. It has higher RDS-on, quite a bit higher RDS-on, but compared to the part that is usually used today in these applications, we can have still better performance. And just like the original example, better performance and increasing switching frequency. So in this case here, we wanted to try to go from 400 kilohertz all the way up to 1.8 megahertz. And this is really what we should, especially if you look at the 1.8 megahertz columns, the reduction in losses is extremely significant when you start using GaN devices. And what is interesting about this example is to show the power density impact. And this is what is the impact at the system level, right? So when you go to 1.8 megahertz, in this particular design example, we were able to go from a 4.7 microhenry inductor to a 1 microhenry inductor. And the way you can do it two ways. You can say, all right, I'm going to use the same size of inductor, keep the same size, and just use a lower inductance, which means the DCR will be lower losses. Or I can say, I'm going to keep the same losses in this inductor and going to shrink it as much as I can. And of course, a designer can choose anything in between, but these are the two extremes. And I think they're very revealing. I put it in the charts in the bottom here. Basically, on the left-hand side, you have the case where we keep the same size for the inductor, and we just see what is the maximum efficiency improvement or reduction in loss that we can get. And it's massive. You go from 2.8 watts down to less than 1 watt. So basically about a third of the losses of the original design. And again, you have increased the switching frequency. So you can have a huge improvement in efficiency and in size. And on the right-hand side, you have the other extreme, which is basically we keep the same losses. How much can you reduce it? And same thing, you can reduce it basically by a factor, more than a factor of 5. So again, you're keeping the same losses overall, and you're saying the inductor what kind of inductor can you use as small to do that. The inductor part numbers are listed up there. They're all part of the same family. And again, 5 times reduction in size. And you can go anywhere in between these two. You can get some efficient improvement and some reduction. Maybe, you can do half and half of it. So that's the real advantage of increasing switching frequency in these applications. The last example I want to talk about is this one here. This is a new reference design that we're working on. It's 9178. It's basically a higher power version of the same topology. This one is using a TI controller, LM5117. You can see the picture of the board on the bottom right. It's actually under test right now, so I didn't have all the final figures. We're targeting more than 98% efficiency. Right now, we're switching at 400 kilohertz for this power level, and this is 30 to 60 volts input and output back-to-back topology. Very interesting board for higher power battery applications. So this is coming soon. I think even probably within a month or so, we should be able to release it. So these are basically a few examples of how GaN can add value in these topologies, back-to-back topologies, which are very commonly used in battery applications. That concludes my presentation for today. I put here a few links for you. The first one is the GaN Talk support forum. We have a very active forum. You can post your questions, and you can also search previous topics on GaN-related design and general issues, general questions about GaN. I encourage you to take a look at it. We actively monitor and try and answer as quick as possible. The second link is the cross-reference search. This is a very interesting tool that I haven't shown today, but I really like it. It's based on a very extensive database of parts, more than 20,000 parts. You can put the silicon MOSFET part number in there, your conditions, and it will calculate the best match based on actual losses, not just RDS on, but actual losses. And I think that's very powerful. And finally, of course, we have a standard selection tool for buck converters for more detailed calculation, as well as the thermal calculator tool, which is a tool I was mentioning when I was showing those comparison between different thermal solutions. So yeah, that concludes my talk for today. I think now we're open for questions.
Okay, so thank you, Andrea. Yep, we're going to start answering the questions that were submitted. And as a reminder, you can still submit your questions by just typing them into the Q&A feature at the bottom of the screen. So the first question we have is, you compare silicon and GaN. We can see for silicon, we have an industrial package, but for the GaN, it is only flip chip. Do you use any special package to integrate it?
No. So in this example, actually, you can see it right here. This is what we did. You can see it on the top side. You see our chip level scale packages, basically these little black dots there. On the bottom, you see the 5x6. Now, EPC has a very extensive product offering of chip scale level packages. They offer the best performance because they're very small, so you can make extremely compact designs, and as I've shown, still thermally very efficient, which minimizes all the parasitics, which is very good when you want to push the switching frequencies. We do offer now also a line of QFN packages, and we will also offer Gen 6 in a QFN package. These are still very high performance QFN package. They have, for example, still an exposed top, so that allows still to take a full advantage of the topside cooling that we offer on our devices. So that's also a very interesting alternative to our chip level scale packages. They allow for a little bit better clearances on the bottom, so the manufacturability is better. So we have a growing line of products that are released and that are in development in this QFN family also, which I have not shown today.
Okay. I guess while you're on that page, it says, what thermal tool did you use for the thermal images?
Oh, this was a thermal camera, IR camera. Yes, I think we use a flare camera. I don't know if I should say. Very commonly used in the labs.
Yeah. Okay. In your example, we can see that you can improve the I guess I think it means increase the frequency, but does using GaN, are you also able to reduce EMC noise?
So EMC noises have lots of sources, of course, we think that you can have very effective designs with GaN even at higher switching frequencies, and there's a few factors in it. Of course, the actual slope is the first thing people think about. When you switch fast, you gotta have faster rise and fall times. And of course, they contribute to higher frequency spectrums. However, if you really what is contributing to EMI are other factors also. So one of them, for example, is reverse recovery. Reverse recovery is a very large contributor to EMI because it's basically a large current that is happening at every switching event, and that is it's a shoot-through event. It goes from the high side and the low side at the same time. So we don't have reverse recovery. So that's one thing that you don't have. The other thing that you have with GaN devices is that they are very linear, because the capacitance, they still change with voltage, just like silicon FET, but they change a lot less. So you end up having very smooth waveforms during these transitions. And so although the average might be faster, you'll end up, when you look at a silicon MOSFET transition time, you'll have areas of the transition time which have higher DVDTs than others. Instead, the GaN FETs are very, I would say, very linear, very clean waveforms. We have example of waveforms on our demo boards, for example, and you'll see it's very little ringing and very stable. The ringing comes down to basically the design of the PCB and the power loops. And actually, this is a good slide to show that, because I mentioned a little bit when I commented, when you use the GaN FETs, they're very small, and you can see that the layout, that the way they do, they have these we can do a layout basically putting the two parts next to each other, making an extremely small loop and really optimizing all the parasitic inductances. And you can see the effect here on the bottom. We try to do the same thing with the silicon FET, but basically they're larger, and the footprint themselves, they're not optimized for that, and how you connect the gate driver. So you end up with a loop that is inherently larger. And that loop is really what creates all those ringing that you see in the switching waveforms, the overshoot at the turnoff. Those are major contributors to EMI, and you can greatly reduce them by using GaN devices and optimized layout with GaN devices. So yes, you can also have very effective EMI designs with GaN, and we have many customers that are in production today with GaN devices at quite high switching frequencies.
Okay. Next is, who is the vendor for the inductor that you are using for the B2B converter?
I believe it's Vishay.
Okay. In case of high voltage flyback converter using GaN, will the high voltage and high frequencies saturate the core of the transformer?
So first of all, we don't have 600-volt devices, so we do not have any parts for high voltage flyback converters. So I would say that's my first answer. But of course, you need to design the transformer appropriately for the volt seconds of your applications. I would say that's the general guideline.
Okay. With discontinuous converters and high switching speeds, core losses are much higher than resistive losses. Is there any better material or vendor recommended for low core loss when using GaN?
We do work actively with manufacturers, and we have reference designs all the way up to 2 megahertz on our website. So I would encourage you to take a look at our high speed DC-DC converters, and there's definitely some inductors there that you can use for these higher frequency applications. Yes.
What optimizations need to be made in a GaN design to ensure optimal switching frequency? And then the second part of that is, what waveforms and parameters are the most critical to optimize?
So can you read that again? It's a long
Sure.
question.
What optimizations need to be made in a GaN design to ensure optimal switching frequency? And
So
then,
optimal switching frequency is an interesting question. I don't have the charts here, but so the way I interpret optimal switching frequency means and it's true for any semiconductor technology. Basically, you have always a trade-off between conduction and switching losses. And if you go very low switching frequency, you're dominated by conduction losses. If you increase the switching free, you're dominated by switching losses. Naturally, there's a minimum in that. So basically, if you take within one technology, if you start from a very small die or a very large die size, so lower the SON, and you shrink it, you will have that for a particular set of condition, you actually have an optimum size. And that means that you also have the lowest possible losses at that particular application for the converter itself. So I think basically this is a figure of merit dependent calculation. But the interesting part, again, I don't have it here, but we ran the numbers for several technologies. The general trade-off, of course, when you have a better figure of merit, which I was showing basically in the comparison between silicon and GaN, you have a different chart. And that means two things mainly, is that you have an overall lower minimum. Now the minimum, probably at every frequency, probably in most of the cases, maybe except at a few kilohertz, is going to be lower losses. But the minimum, the best you can do, is going to be lower losses because you have a bigger figure of merit. And this minimum is also shifted to a smaller device and a higher frequency. So those are all things that basically play an advantage towards GaN. The second question was more about how you actually do it physically, right? How do you do a layout like that? So again, you can design a converter that is more efficient and lower losses, basically, and higher frequency. And what you do need to pay attention, of course, the device itself, by itself, if you look at it, it actually looks great, right? But then you got to put it on the board. And that's where we do have, of course, a lot of material on our website to take a look at. I encourage you to take a look at it because, of course, to take advantage of this, a characteristic of a device, you need to switch faster. And switch faster, I mentioned already, at the end, you're fighting against all the circuit parasitics. So if you lay down your board, I would say in order of priority of things that are important, there are basically three areas. It's a 3-pin terminal, so there's 3 things you got to think about in terms of inductances. So there's the source inductance, the drain inductance, and the gate inductance, let's call it this way. So the most important one is the source inductance. That's a common source inductance. That's the inductance that is in common between the gate loop and the power loop. The reason it's important, because effectively, if you run the calculations during the transients, you're having this high DIDT in this inductance, and it's getting voltage out of your gate. So you're basically like having a higher gate resistor, you're slowing down your device. So it effectively puts a limit how fast you can switch. And that's why a lot of silicon devices are trying to get higher frequencies. They have what they call a Kelvin source. That means there's a separate wire bond to connect to the source to eliminate the package contribution to that common source inductance. The advantage of GaN is there's no wire bonds. You have direct access, basically a few microns away from the actual source of the gate. And so you have the minimum possible common source inductance. Now, when you put it on your board, you need to make sure that you don't create common source inductance. So I think that's the first priority. Way to do it is, and you can see the example here, I like this slide for that, is basically if you look at the GaN device, you have the power loop going in this vertical direction and the gate loop going 90 degrees of it. So that means you have basically no overlap. So that's what the first thing you got to do if you want to switch effectively at high frequencies. You got to make those 2 loops at 90 degrees and minimize the common source inductance. And when I mean 90 degrees, it means to be really next to it. It can't be up here or down there, because then it's not 90 degrees anymore. It's 45, right? So that's the first one. The second one is the power loop itself. So I mentioned that a little bit, especially for EMI, that contributes to all the ringing and losses eventually. And to do that, we have a lot of guidelines. We recommend, and you can do this really only with GaN devices. We put the 2 devices here next to each other, high side and low side, and the capacitors right here. These are the bus caps. And the loop is basically the minimum physical loop you can make. It goes on the top layer, down 1 layer. We don't want to go to the bottom. We want to go just to the inner layer underneath and go back up. So that creates the minimum power loop inductance possible. And again, for example, in the silicon FETs, we're not able to do it because we had to go underneath. So you have the whole thickness of the PCB versus just the first inner layer. Some people, when they do low speed design, they'll do a lateral layout. So the capacitors are placed next to the devices, and all the current path is on the top layer. So that's the worst case scenario. So again, optimizing the power loop, and we have a lot of guidelines how to do that, but basically you put the caps right next here and then you close the loop right underneath that. That is the best way to do a layout for high switching frequency. And the last loop is you want to minimize the gate loop inductance itself. It's still important, although it's third. And there the concept is the same. In this case here, you have the gate driver right here, and you want to use a similar concept. So you have a trace that goes right there to the gas. It's very, very small distance. And then right underneath, you come back with a little plane and close the loop on the gate itself. Again, these are, I think our company has done a lot of work on this. These are really nice layouts, very simple to implement, and they can really perform at extremely high frequencies.
Okay. Next is, can we consider the GaN FET as small enough to be a lumped component within the operation frequency range for optimization?
I would say yes. For example, in our SPICE models, we don't provide any parasitic inductances because they're so small that typically the main contribution to parasitic inductance is actually from the layout. So the component itself, I would say yes, but the layout usually is not. Even optimized layouts are not ideal layouts. So I think those should be considered in more detailed simulation. But detailed simulations are tough, so there's a limit how much you can get out of a simulation. So, but if you want to do a detailed simulation, yes, you need to consider, I would say, the layout components of it more than the device itself.
Okay. GaN have small capacitors, so can the majority of MOSFET drivers be used, or do we have to be careful about that?
Well, that's an advantage. I would say there's no problem in using a higher output driver if the concern is just the output. So yes, we have very small capacity. What that means basically, that's what I was showing in the slides for the Gen 6 is you have less gate driver losses. So that's very good for the gate driver. You might be able to use a smaller output gate driver basically. But you do have to be careful about the gate driver. I think it's not about the gate charge. The main difference is the voltage rating, right? So that is definitely something to be careful with. The GaN devices are GaN devices, but they're all pretty much similar in the industry, are rated to a max of 6 volts, and you need to run them at 5 volts roughly. And so that means you do have to be careful with the gate driver that you're using, so that you have a stable gate drive signal, and of course that you do not go too high or too low. You know, a lot of silicon FETs, they're used at 10 volts, for example. So it's there are, I would say, 2 ways. First of all, there's a growing list of dedicated gate drivers for GaN, which not only take care of this particular topic of controlling that gate drive voltage, but also very strong in terms of DVDT they can survive, because that's the thing, you know, you use the GaN because you want to go fast. You want to make sure your gate driver, which will see that voltage transient on the switch node, is able to withstand that. So there's a growing list of ecosystem there with gate drivers and controllers that are specifically tailored for GaN devices. But you can also use more traditional GaN silicon gate driver, as long as the things that I mentioned before, which basically is being the ability to control that voltage to around 5 volts and not over 6 volts. So that means appropriate under voltage lockouts, and yes, you have to be careful to DVDT immunity, because if you want to switch fast, the gate driver needs to survive.
Okay. This one, I think you addressed a lot of these, but I just want to give you a chance in case you want to add anything. So the question was, what challenges do most people face while designing with GaN, and how to tackle them?
I would say really it's you know, if you look at a data sheet for a GaN FET, it looks very similar to a silicon FET. So the charts are the same, the things are the same, the numbers change. And I think that's basically what the challenge is. So the actual numbers are changing. They're much smaller in terms of all the capacitances, for example, which means you end up switching much faster, and the gate part. So I think the first challenge is just making sure you select the appropriate gate driver and controller. I already mentioned that, right? So you have to make sure you select the right part. And then it's layout. Layout is very important, because again, yeah, you can make a bad layout, but then you're going to slow it down, and then you might as well use a silicon FET. So you want to make a good layout, and that's where I would say the biggest challenge is. And it's not hard to make a good layout. It's just that if you don't think about it and you use the layout you were used to before, you will get these high parasitics when you start switching fast, will create ringing all over the place. So I really encourage everybody to look at our website. We have some very clear guidelines. We also have all of the reference design. They all use similar way to make these layouts. But the layout part, you just have to implement it in a way that really takes care of the things I mentioned. And then after that, it's pretty straightforward. The other thing maybe to mention is these are very small devices. So you need to make sure that your assembly house can handle these fine pitches. Yeah, those are the main things.
Okay, great. Okay, so that was the last of the questions, unless anybody has anything else last minute they want to shoot in there. But If not, I just want to say thank you to Andrea and thank you to everyone for attending today's webinar. If you do have any other questions, you can certainly send them in to us at info@epc-co.com. You should receive a follow-up email within the next 24 to 48 hours, which will have a link to view the recording of today's webinar, as well as a copy of the final slide set. For those of you attending APEC, please stop by and see us in booth 732. We'll be there in another week and a half, 2 weeks, I guess that is. And then lastly, this summer, we will once again run our Summer of GaN webinar series, and the focus is going to be on reliability in real world applications, including DC-DC conversion, solar, LiDAR, space, and motor drives. Once that schedule is finalized, those details will be available on the website at epc-co.com, or if you are already signed up to receive our newsletter updates, you'll be notified directly with those registration details. So again, thank you again for joining us and have a great rest of your day. Thank you.
Bye-bye.
Bye.